Hello everyone, this is Christina here, and for this Navratri Shiksha Utsav, I am here to explain about the Euler's remainders theorem. So before you go on with this video, you should have a slight understanding about the concepts of remainders. And if you have done remainders, you might have come across binomial theorem, Wilson's theorem, Fermat's theorem, and all such. Okay, so Euler's is one such important theorem which is definitely going to either bring down the complexity of the problem to a higher level, okay, or it's definitely going to help you solve the complete question. Okay, so remember, okay, if it's possible, it'll help you to come to the solution, or sometimes it'll help you to bring down the complexity of that problem. Okay, so let's now go on with Euler's remainders theorem and figure it out. First of all, before knowing that, you should know what is this Euler's totient function. And from now onwards, I'll be referring to this Euler's totient function as phi of x. So how do you define phi of x? Phi of x is the number of positive integers less than x which are coprime to x. The meaning of the word coprime is if I say that a and b are coprime to each other, then it means that the HCF of these two numbers is going to be 1. So let's take a small number 9. And I know that the positive integers of 9 below it are 1, 2, 3, 4, 5, 6, 7, and 8. Now let's see how many of them are coprime to 9. 1 is coprime to 9, 2 is coprime to 9, 3 is not because 9 and 3 will have 3 in common. 4 is coprime to 9, 5 is coprime to 9, 6 is not because again 9 and 6 have 3 in common. Again 7 is coprime to 9 and 8 is coprime to 9. So 1, 2, 3, 4, 5, 6. There are 6 positive integers less than 9 which are coprime to it, which tells me that phi of 9 is equal to 6. Okay, for small numbers like 9, 10, 12, it's easy for us to list on all the positive integers below it and figure out which are all going to be coprime to it. But as the numbers become large like 1000 and all, will you write down all the terms and then figure it out manually? Not possible, right? So let's take the small formula. Phi of x can be got by x into 1 minus 1 by a into 1 minus 1 by b into 1 minus 1 by c into 1 minus 1 by d and so on. Okay, where a, b, c, d, all of these now are going to be prime factors of x. So 20 can be expressed as 2 to the power 2 into 5 power 1. So the prime factors of 20 is going to be 2 and 5. Okay, now let's try to apply it in that phi of x formula. So phi of 20 is going to be 20 into 1 minus 1 by 2 and into 1 minus 1 by 5. So this gives rise to 1 minus 1 by 2 is 1 by 2 and 1 minus 1 by 5 is 4 by 5. So 20 into 1 by 2 into 4 by 5, that's going to be 8. So by this slide now, we know how to calculate the Euler's totient function, or we know how to calculate phi of a particular number, phi of x. Okay, so now you randomly take a few numbers and then try getting the Euler's totient function of those numbers. Okay, and here for phi of 20, we have come down to 8. So we'll remember this for the next slide. Phi of 20 is going to be 8. Now, what does this remainders theorem say? Okay, so Euler's remainder theorem tells me that n to the power phi of x, the remainder is always going to be 1 when divided by x. Okay, and this is possible only when x and n are going to be coprime to each other. Now let's take a small example here. To find the remainder of 43 to the power 1600 divided by 20. First condition I should notice, are 20 and 45 coprime to each other? Yes, they are coprime to each other. The HCF is going to be 1. So now I can go on to try applying my Euler's remainder theorem. And for that now I need phi of x, phi of 20. And we in the previous slide have seen that phi of 20 was 8. So here, as per this Euler's remainder theorem, I can say that 43 to the power phi of x, that is 43 to the power phi of 20 or 43 power 8, when divided by 20, the remainder should always be 1. Now, how do I express this whole thing in terms of 43 to the power 8 to the power something? So 43 to the power 8 whole power 200 gives you 43 power 1600. So when you divide that by 20, I know by Euler's remainders theorem, 43 power 8 divided by 20 remainder is 1. 1 power 200 is going to be 1. Got it? So this is how we apply Euler's remainders theorem. Now let's take one more small example. Find the remainder when 30 to the power 496 is divided by 17. Now you will see that for this, okay, 30 and 17 are co-prime to each other. So I can look out to apply Euler's theorem. And before I go and apply Euler's theorem, I need Euler's totient function of 17. So 17 here, it's a prime number. So I know that all the positive integers below 17 have to be co-prime to it. Okay, so there will be definitely 16 positive integers below it and all will be co-prime. Or I can also apply this totient function formula, that is 17 into 1 minus 1 by 17, as 17 is the only prime factor of 17. Okay, so phi of 17 is equal to 16. Now, by Euler's theorem, I know that 30 to the power phi of 17, which is 16, when divided by 17, the remainder should be 1. Okay, now I can express this whole thing as 30 to the power 16 whole power 31. See, 16 into 31. This will give you here 6. Then 1 plus 18 is going to be 19. 3 into 3 is going to be, 3 into 1 is going to be 3, plus 1 is going to be 4. So you get here 30 to the power 16 whole power 31 is 30 to the power 496. Okay, so that whole thing when you divide it by 17, by Euler's remainders theorem, 30 power 16 by 17, remainder is 1, 1 power 31, the remainder has to be 1. Okay, right. So we have seen two good examples for application of this Euler's remainders theorem. Now let us have a small note. We saw that 17 was a prime number. Okay, and we know that all the positive integers below any prime number are going to be co-prime to it. So for any prime number, phi of p will always be p minus 1. For example, you take two prime numbers, 3, 5. Okay, the positive integer below 2 is 1 and 1 is co-prime to 2. So phi of 2 is equal to 1. Now for 3, 1 and 2 are the positive integers below 3 and both are co-prime to 3. So phi of 3 is equal to 2. Similarly, going on with 5, 1, 2, 3 and 4. All of these are co-prime to 5. So phi of 5 is going to be 4. So you'll see that phi of any prime number is equal to that number minus 1. Okay, because all the positive integers below that particular number will be co-prime to it. So with this in mind, okay, we can come to Fermat's remainders theorem. So as per Euler's theorem, we know that n to the power phi of x when divided by x, the remainder is always going to be 1 if n and x are co-prime to each other. Okay, so what if x becomes a prime number? What if x becomes a prime number? So phi of that prime number will be nothing but p minus 1. So from here I can say n to the power p minus 1 divided by that prime number p. The remainder is always going to be 1 if p is prime and also co-prime to n. Okay, that we shouldn't be missing out. It has to be definitely co-prime to n. Right? So with this we come to the end of this particular video, my dear. Okay, take around 10 to 15 problems on remainders and try to apply Fermats and Eulers. That should be more than enough for you to get those theorems into your heads. So before I wind up with this video, I would like to wish you all a very happy Navratri and also all the best for the upcoming days of your preparation and for the exam. Okay, right. Thank you.